welcome. This session is actually, so Nicole Hansen is our facilitator. She's going to tell you a little bit about herself in just a couple of seconds, but the title of this particular workshop is, or session is, More Than Patterns, Cultivating Coherent Understandings from Mathematical Standards for Mathematical Practice number 7 and number 8. So Nicole has a chocker block session ready to rock and roll. So I'm going to turn everything over to her. But at the end, I'm just going to do a little bit of a plug for all learners and the AOE again. So Nicole, the show is yours.
Great, thanks so much. So good evening, or I guess it's still afternoon technically, but I'm Nicole and I am the new math coaching coordinator at Charlotte Central School. I actually just moved to Vermont at the end of August. And before that, I've been teaching middle school and high school math in Hanover, New Hampshire, and in Boston, Mass. And I would love to just start off with some introductions. And I had this in the chat, but I think with this number of people, if people are willing to just unmute and share, that'd be great. I'd love to hear people's names, the school or organization you work for and your position there. And then I have the 8 standards for mathematical practice here from the Common Core, and I'd love to hear which one or ones are your favorite and why. So I'll give people about a minute to think about that, and then we can share.
It's number 1, hands down. It's number 1, helping, not helping, but actually giving something to kids to chew on, and that they stick with and figure out ways to enter into the tasks and scaffold when it's necessary, but not before it's necessary.
Absolutely. I gave you all a question that I think I have trouble answering myself. I love all of the math practices, but I've spent a lot of time thinking about math practice 7 and math practice 8. They're ones that are definitely close to my heart, and also ones that I think are really powerful in the math classroom. As Brendan was saying, thinking about structure and patterns and how things are organized. And so I think that that's so essential in math, but I also think it's something that these 2 practices can be a little bit confusing to teachers and to students, and thinking about how might they be related, how might they be different. And so that's really what we're going to be diving into today. So goals, the first one is clarify how those 2 math practices are both different and related. I'm also going to describe actions that students take when they're looking for, making use of, and expressing structure and regularity and repeated reasoning, those kind of action words that come up in each of those standards. And also provide some examples of how students would use these actions with specific tasks. And you'll see in the examples that I give, I am kind of living in the middle school area, which is probably my the time where I've spent the most, but we'll have some elementary examples also in the handout that you'll see later. And so the agenda then, we're going to start by doing some math, and then I'll share some common misconceptions, and then this framework. So that's kind of our plan for today. All right, so I have 2 problems here that I'd like to give people about 5 minutes of private think time to try out themselves. So if you have a piece of paper or a mini whiteboard or something close to you, why don't you grab that, and we'll take a couple minutes to solve these. I'd like you to try to solve these problems at least 2 ways. It could be ways that you think students might approach the problem. It could be ways that you think you would approach the problem. And as you're working, I want you to think about, okay, how might you be using standard for mathematical practice 7, looking for making use of structure, and or standard for mathematical practice 8, look for and express regularity and repeated reasoning. So take about 5 minutes to try the problems, think about those, and then we'll all come back together and talk about it a little bit. This is the time where I really wish that we were in person and I could walk around and see what people are doing, but I'll just sit here and wait for a couple more minutes. We were just looking at these two problems, and I'm hoping maybe we can start off with problem one. And if there is a brave soul who'd be willing to share, what's one way that you thought about this problem? How did you figure out the cost of an ice cream cone?
Well, I know I was boring. I went right to assigning variables and writing equations, and I just went with my, I'm a linear sequential learner. I'm totally in there. So I would love to see if someone had a more artistic, creative way of solving that one.
Yep, nothing wrong with writing a system of equations and solving it, but as we just heard from Steve, I'll go ahead and ask, did anyone think about it a different way? Yeah, go ahead.
I started sketching them out and thinking time's going to run out before I sketch these down. But by doing that, I noticed one of them, working on problem one, I noticed the patterns with the cake and ice cream, that there were 3 sets of those. And I figured that would be a clue. So I started just playing around with the sets ideas and looking to see what I could pair up, what I could eliminate. So.
And did you find anything that you could eliminate there?
I was writing rather quickly, so it's a little harder to see, but I paired up the first and the third set. The 8 equals cake and 3 cones, and the cake is equal to a cone and $2. And essentially did substitution and found out after that substitution, I arrived at 6 is equal to 4 ice cream, $6 is equal to 4 ice cream cones. So each ice cream cone is $1.50. And then I did as I expect people to do, or try to get people to do, go back and check to make sure that it made sense in all the equations and so on.
Nice. So it sounds like kind of the key to your solution here was noticing that you had that single cake at the bottom and then could do some replacement or substitution in that first equation.
And the 3 sets became part of a later, it's not what I worked on initially, but it was something that, was easy to check when
Yeah.
I found out the value of the set of a cone and a cake.
Great. Did anyone have another way that they thought about this problem?
I'll piggyback on Pauline. I did the same. I went with substitution. I saw that the cake in the third equation was independent and knew that the ice cream add $2, just substituted, knew that I had 4 ice cream cones and $2, subtracted and figured out what the ice cream cone was and then substituted away and good.
Nice. Yeah, this is a problem that I used with my 8th graders kind of as we were leading into a unit on algebraically solving systems of equations. And the method that both Pauline and Brendan talked about with that substitution was definitely one that came up. Another method that came up was students noticed that there were 3 ice cream cones in the first 2 equations in both of those. And then also 1 cake in each of those, which allowed them to do a little bit of elimination, where if you think, okay, the difference between those first 2 equations is 2 cakes, and those 2 cakes must cost the difference in the cost, $7, and then you can work from there. So that's another way that I've seen students solve this. Do people want another minute or 2 to think about problem 2 before we talk about it, or do you feel ready now? Okay, seeing a thumbs up. All right, is there anyone who's willing to tell us how they approach problem 2 here?
I'll jump in. I initially looked at this and thought about first, it was just it's add 2, then realize, oh, well, the 6th number in the pattern will be a 1 again. And so there's only 5 possible digits. The sequence is 5 digits, 217 as a multiple of 5. There's 43 iterations. So like the 215th number will be a 9, I think. And the 216th a 1 and 217th a 3.
Nice. So you notice like this cycle of 5, 1, 3, 5, 7, 9, 1, 3, 5, 7, 9 as you're thinking about the last digit
Yes.
in the sequence. Great.
Yes.
Did anyone else think about it another way? Yeah, go ahead, Pauline.
I essentially reasoned through to that point, but I didn't bother to find out how many iterations there would be. I just knew that I needed the remainder. So I just did thinking about the remainder being 2 and then identified the digit.
Can you say more? What do you mean by the remainder of 2?
So I set up just a traditional division algorithm or division setup and, jumped right to the remainder, knowing that I would get 215 would be the closest, but not over multiple of 5. And so what I was concerned with in this wasn't the quotient, it was the full quotient, it was the remainder.
Got it. So you did 217 divided by 5 because of that same sequence of 5, but then you just focused on the remainder and maybe didn't do all the division out to figure out where you would be in that sequence.
And then I went back and checked, much like the person before me said that, check to make sure, okay, is this going to work like 6th or 7th one? Will that work? And verified that I was on the right track with that one.
Great. Did anyone have another way? Yeah, go ahead.
I saw it as doubling, I started when it said the 217th, I'm immediately going, okay, I got the first number, the second number, the third number, the fourth. And in my head, I'm sitting there thinking of 2, 4, 6, 8. And I'm like, oh, it's 1 less than doubling. So just double 217, take away 1, there's your 433. So that's
nice. So you kind of found what's a rule that's always going to work.
Yeah, like I said, when I saw the 217th, that caused me to look at 1, 3, 5, 7, 9 as first number, second number, third number, fourth. And then because the doubles, it just kind of popped out. Yeah.
So to find like the 9, the 5th number in the sequence, you did double
Yep.
of
Take a
5,
one.
that's 10, and then -1 is 9.
Yeah. Yep.
Cool. Great. I think we'll go ahead on to the questions here. We've heard a couple different strategies for each of those. Let's start with math practice 7, look for and make use of structure. In the kind of strategies we just heard, does anyone think that they or someone that they heard from looked for or made use of structure? And what does that kind of mean in this context? Anyone have a thought? Go ahead, Pauline.
The structure, what pops into mind a lot for me is the algebraic thinking, but the structure here is represented by like the icons. And so looking for what's alike and what's different in problem 1, and noticing the only time that a number value is introduced other than the totals in the first 2 equations is in the 3rd equation. And so being able to look at things like sets, or like the last way you described for solving, being the differences between them is part of looking at the structure. In a way, there's repetition in that. So I'm not sure that rises to looking at number 8, but definitely the structure of the equations and being able to identify there's really 2 distinct elements and a bunch of different combinations with that.
Yeah, absolutely. And I'm happy to open it up to math practice 8 also. I know you touched on both of those, Pauline. Any other thoughts on what these could mean, either in general or in the context of these problems? All right, I know that I'm kind of asking for thoughts before we really get into some serious definitions. So I think I'll go ahead and share kind of the next portion of this presentation, and then we'll come back to our understandings of these 2 practices. So we talked about those things. This presentation comes out of some work that I did really from 2016 to 2018 with Dr. Hilary Kreisberg, who works at Lesley University. She's the director for the Center of Mathematics there. And we met at a conference in the Boston area and realized we were both kind of thinking about these 2 math practices and really trying to get a sense of what teacher understandings were and how these work in the classroom, and really trying to clarify. So we worked together for a couple of years thinking about these 2 practices. And part of our work was starting to survey teachers to see what they knew about these practices, kind of how much professional development they had around them. And so in 2017, we surveyed about 242 educators and administrators. Most of them were from Massachusetts. Most of them were classroom teachers, but kind of had a wide range. And one of the questions that we asked those teachers is, what do these 2 math practices mean to you? And we gave them the same language that we gave you all, or that I just gave you all. Just that 7 is look for and make use of structure, and 8 is look for and express regularity and repeated reasoning. And what we did with all those responses is kind of coded them to see what were the common themes that came up. And we found a couple surprising, or maybe not so surprising, things, which were first, that there was a lot of overlap in terms of how people describe these 2 standards. So you can see here for math practice 7, 18 people talked about this idea of generalizing, and 73 people for math practice 8 talked about generalizing or making a conjecture or creating a rule, discovering algorithms. And we continue to see these overlaps. Using and applying prior knowledge or experience came up for both of them. Forming connections between mathematical ideas, making connections was a really big overlap. There were also a lot of people who really didn't know. They said, we've been working under the Common Core standards for, I think, at least 5 years at this point. We have these on our walls, but I'm not totally sure what they actually mean. And finally, we also had the most common response for both of those was something about patterns. And so we'll come back to this idea of patterns after we dig in a little bit deeper. But it was really interesting to see, okay, people are using this word pattern all over the place, but they're really talking about patterns for different things and in different contexts. And that made us think maybe it would be helpful for educators to think about what do they really mean by pattern in different contexts, and is there other language that we might be able to use there? So I want to dig a little bit deeper into these two practices, and then we'll come back to, okay, what does pattern actually mean? And so we got these responses. We heard people had really different ideas. And so we started to look deeper into what the research says and who was writing and thinking about the practices. So we started with the elaborations that illustrative math did for the Common Core standards, including the math practices. And then we also read a bunch of other books that all touched on what these math practices meant. And from reading these books, we felt like we got to a good understanding of what math practice 7 and 8 were not. That's really where we started. And so two ideas that had come up for math practice 7 around structural thinking in teachers' responses were that math practice 7 was about organizing. So using a routine or making sure a lesson is structured properly, or organizing your work and showing problems step by step. And we were pretty clear that this was a common misconception. It's not actually about how you organize your lesson or your work. There's something else going on there. And it's also not about deciding how to solve a problem. So these were two kind of common answers that we think were misunderstandings of the practice. Similarly, for repeated reasoning, we had some teachers who thought that math practice 8 was all about practice, doing the same thing over and over again. Being able to use a procedure with high accuracy because you've been doing it a lot. And we also had teachers who kind of misunderstood math practice 8 as they needed to repeat themselves or remind students of things, kind of say the same thing over and over again. And these were the two common misconceptions that we had there. So using kind of the research that was out there, we were able to rule those two or these common misconceptions out. But we still weren't super clear on what math practice 7 and 8 were. So what we started doing is just like we did earlier in this session is we started doing problems where we felt like, oh yeah, there's something going on here with patterns or with structure, and started to think about what were we actually doing to solve those problems. And so from that, we came up with kind of our vision of what these two practices were. So for look for and make use of structure, we split it into the two parts. For looking for structure, that really involves the problem solver noticing behaviors, relationships, organization, characteristics, and traits of the mathematics. So earlier, when we heard someone noticing that, oh, we had just a single cake that we could replace, that was starting to notice kind of the organization or the characteristics of those relationships that we were seeing. And then once you do these noticings, the second part of math practice 7 is then either connecting those noticings to prior knowledge and or manipulating or reorganizing the mathematics in order to find a way to solve. So when we did the substitution there with that cake, replacing it with the ice cream plus $2, that would be an example of kind of reorganizing the math in a way that makes it more useful. An example of connecting those noticings to prior knowledge might be looking at that cake and ice cream visual and saying, hey, this reminds me of what I know about a system of equations, and thinking about how have you solved those in the past? How could you connect that and organize it that way? For math practice 8, we have to look for regularity in repeating reasoning involves the problem solver simultaneously noticing and organizing repeated calculations or actions. So when we're thinking about that sequence of odd numbers, maybe I do write out 1, 3, 5, 7, 9. And then on the next row, I have 11, 13, 15, 17, 19. And I'm organizing those numbers so I can see that clear pattern of 5 numbers at once is a cycle. And then you have to generalize. So from your organization of repeated calculations or actions, then you can develop a rule or conjecture. You can say, okay, I know that every 5th number is going to end in a 9 in my sequence. That's our overall rule there. And to think about supporting students in this reasoning, for each of those kind of parts of the practice, we came up with some questions that students or you all, anyone who's solving problems might ask themselves. So I'll just put these up for a minute and let you all take a look here. And what you might notice in these questions is there definitely is some overlap. Specifically, if we're looking at the kind of looking for structure, thinking about how something's behaving or relationships or characteristics, that's really related to this idea of expressing regularity in repeated reasoning, where you're trying to create a general rule about the relationships there or about the behavior that's there. And so that's part of the reason why it seems like these two practices really overlap and go together. I know this is a lot to digest, so I think what I'll do now is everything that or most of what I just said, along with some actual examples, are in this handout. And Sandy, if you could put the link to the handout in the chat. I want to give people a couple minutes to look at this. Oh, and great. And then, whoops, sorry. We'll come back and talk about kind of what are your takeaways so far and what are your questions. And you'll see when you open that, the first page of the handout is that same kind of splitting each practice into 2 parts. And then the second and third pages have the questions that you just saw in different colored fonts, and then example problems where people might be, or for how someone might approach the problem using those questions and using the math practices. And I'd love to hear kind of any takeaways or questions you have at this point.
I think major takeaway for me as a 4th grade teacher in the math practices is how to embed them in a lesson cycle, and the idea of an engagement image or task or instructional routine that launches a lesson is an ideal time to focus on the math practices. It's also evident that it can't be me talking, that it has to be the students positioned to do the lifting and load. And I think piggybacking on Steve Linewad, just asking purposeful, and I think Ryan posted it, purposeful questions, and not giving any solutions, and letting the struggle happen, and labeling the practices when they happen, annotating them for the students to show them that they're happening.
Yeah, absolutely. And as you mentioned, like mathematical routines as a great way to really engage students in the math practices. If you haven't read it before, one of the books that we really referenced in thinking about this is Routines for Reasoning by Grace Kalamanek and Amy Lucenta. And their math practices are their routines are specifically tied to math practices, including ones for math practice 7 and 8. So that's a great resource to check out. Yeah, other thoughts or questions?
One of the things that I find, in trying to draw kids out about their explanations, especially students who have difficulty communicating their thinking, speech and language issues mostly. The frustration level in the beginning is very high for them, but as we do it more often, or as they get used to it, some students are starting to be able to explain what they're thinking more. But I wonder about pushing too far. There's a balance between pushing too hard and too far, and sometimes without a lot of time to like think through some of the things that might come up, that becomes hard. But I like trying to draw out as many different ways of approaching something as I can with students.
Yeah, absolutely.
And also to piggyback on that, a lot of, especially my ninth graders this year, very, very weak number skills. And so I have the luxury of kind of defining what it is that I'm going to cover in the year. And I'm trying to do some basic algebraic steps or concepts, but I'm starting out just with number reasoning, looking at factors and multiples and working with manipulatives and stuff like that, and to try to get kids to see patterns in how numbers are formed. I mean, not all of the kids can recognize an even number right now, and so the range, I mean, it's the same in any mainstream classroom too. The range of abilities and number awareness and skill level just creates difficulties. Let's put it that way.
Yeah, and I think a lot of that early number sense really is about structure, thinking about how numbers are made up, or having noticings about how numbers are related to each other or what's similar or different about them is so important.
Yeah.
So I think I'm going to give you all a chance to try out some of these questions and trying to funnel your thinking maybe through a particular practice yourself. So let me just share my screen again. We have another problem here, which is write an equation to represent the following relationship. And I love to have you try to think of this at least two ways, if not three ways. How might someone approach this problem if they weren't thinking structurally, or if they weren't using repeated reasoning? What might that look like? Versus how might it look if someone was thinking structurally with Math Practice 7 or with repeated reasoning with Math Practice 8? And as you maybe try those pathways, try asking yourself some of those questions there, like how is this table organized, or is there a calculation that I could do over and over again, or some of those types of questions. So I'll give people a couple minutes to try this problem out, and then maybe at 5 we'll continue chatting about this. All right, anyone want to start us off with what's one way you approach this problem, and did you feel like that approach didn't use the math practices, use Math Practice 7 or use Math Practice 8?
Well, I can go. I don't mean to dominate.
No, go ahead.
One of the things, I'm looking directly at what you asked, without using practices 7 or 8, I'm not sure how I could approach it without, because I was trying to start there, and everything I was doing, even when I was trying to think what kinds of things would I notice that might not lead to a solution, I'm still looking at how the table's organized, how what's happening as you go from one number to another. So I think everything I did ties back to those standards. So one of the things I did trying to avoid the, slope-intercept formula at first, was I was noticing in the Y column, we've got, I skipped over the 0th entry, or the when X is 0, but I noticed that in the when X was 1 or 2, the tens digit in the Y value matched what the X value was. But it didn't in the third and when X was 3 or 4. So that time it was 1 less than the X value. And then I got curious about what would keep happening as I went further. I didn't test that out, but then I started to note that's when it really popped that the Y values were increasing by 5 and the X values were increasing by 1. So describe those, and I went on and I did go to slope intercept formula and some other statements and so on, but I'm not sure how to which of the standards would be reflected by my noticings, but because right now I'm having trouble differentiating between the two.
I think you bring up a couple good points. The first one that really jumps out at me is you were saying like you weren't sure how to approach this without using math practice 7 or math practice 8. And one of the reasons I like this example to think through is that this is a pretty standard 8th grade math problem, right? We're not veering away from the curriculum. You could see this in, a worksheet or something that you have that you're just kind of using. And even within that, we have the opportunity to be using math practice 7 or math practice 8. And then I would also say that with those questions that you started with, that sounds more like math practice 7 to me, to think about how is this organized? What are the relationships here? How can I use what I'm noticing to make the rule as you did? Whereas math practice 8 would probably be thinking more about, is there some way I can do a repeated action or find repeated calculations that I could then generalize? So I'm going to show some ways to approach this in a minute, but I would love to hear if there's anyone else who thought about this a different way first.
Can I ask a quick question though? So if I were working through with the repeated reason, noticing there's a pattern with the mathematics that you're adding 5 each time in the Y value, and at the same time adding 1, but I wasn't able to go beyond that. Is that still like an emerging level on using the repeated structure if I wasn't able to get to a rule generalizing?
Yeah, I think you're like right in the territory where these two things overlap. I think key to be able to say, oh yeah, I'm doing math practice 8 is being able to use your repeated reasoning to get to a generalization. So I will actually jump ahead for a second. I would say that your approach is similar to one way I was thinking about how you might use math practice 7. So starting off with what are the characteristics or traits? Something that you might notice is when X is 0, Y is 11. How is it behaving? I notice, as you were just saying, as X increases by 1, Y increases by 5. Then you're maybe making a connection and saying, okay, it's linear. We have a constant rate of change. Mm-hmm. And then relating this to what you already know. Okay, if you know that linear equations can be written in the form y equals mx plus b, where m is the slope and b is the y-intercept, then you can kind of put those two numbers into the equation. And I would say that this is structural thinking, and it's a little bit different than this process, where I think often or sometimes you'll see students who have done a whole bunch of these problems. They see this and say, oh, I'm just going to do the same thing that I've learned to do for the last 3 days. All the problems look like this. And say, okay, I've learned that this is how you calculate slope, plug in the numbers. I found my slope is 5. Then plug in the slope into slope-intercept form, solve for the y-intercept, you have the y-intercept.
Okay.
I think that this is similar to what you described doing, but this is much more like plug and chug, not having a deep understanding, whereas what you described about actually looking at the table and thinking about the relationships would be, in my opinion, more actually using that math practice 7, even though you kind of end up in the same area.
Okay, thank you.
Yeah. Thoughts or questions about that, or other strategies for how people approach the problem? Do you all want to see the math practice 1, math practice 8 approach as well?
Yes,
Okay.
please.
So for 8, we can start off with this question: is there a way to organize my calculations or actions so they always look the same? So maybe a student starts off by thinking, okay, trying to figure out, okay, what can I always do to X to get to Y? So in the first row, I noticed that if I add 11 to the input, I get the output. Does that always work? 0 plus 11 is 11. That's good. 1 plus 11 isn't 16 though. Okay, so that rule or kind of repeated calculation isn't going to work. So maybe a 2-step rule will always take me from the input to the output. Will that work? And maybe the student plays around a little bit and realizes, oh, 5 times whatever the input is plus 11 is always going to give me my output. 5 times 0 plus 11 is 11. 5 times 1 plus 11 is 16. 5 times 2 plus 11 is 21. And so can I create a general rule or statement that describes how a behavior or relationship is always organized? Say, okay, to get the output, I always multiply the input by 5 and add 11. I can write an equation for that. And then rather than using that slope-intercept form, maybe this is a student who's never seen slope-intercept form before. They haven't yet been introduced to linear equations and delved super deeply into it. They might still be able to use this repeated reasoning and kind of experimentation to derive an equation or a rule. Does that help to clarify, at least in this case, how math practice 7 versus math practice 8 approach might be a little bit different?
Yes, it does for me anyway, but it also raises a question.
Yeah.
So in the curriculum, when this is what you're working on, identifying this, there's each kid is going to get to the aha stage. I can use the rule kind of at different points. And then it becomes like, if you're working on this in 8th grade, you come to 9th grade algebra and you're working on reviewing some concepts, then that deeper, it's harder at that point to find out if that understanding is deep enough. So at the point with 7 and 8, I think we're working to get students so they can use this, but eventually keep applying that generalization, like the one that you're showing here, that idea that we can create that equation. Do we need to keep probing for that deeper understanding? Maybe that's I don't know. I think that's kind of a too broad a question to cover right now, but it's the wondering I'm having.
Yeah, I'd love to open that question to the room. I think if I try to rephrase what you're saying and tell me if I'm correct, you're saying, especially by the time students get to 9th grade or to high school, they might have already learned or been exposed to some of this kind of slope-intercept form procedural stuff or moderately procedural stuff. And at that point, it's harder to tell if a student can really understands what's happening and could do something like math practice 7 or math practice 8, or if they are kind of shortcutting into solving this problem without doing that deeper thinking. And then your question is kind of, if they are short, like how can you tell if they're shortcutting, and if they are, what do you do about that?
For years teaching Algebra 1, I mean, one of the quotes that stands out is in working on a beginning linear equation, the beginning of a linear equation unit and going over slope, kids were like, oh, We did slope all year long last year. Why do we have to do it now? I already know how to do slope, yet they couldn't reason through on a situation where slope would be a natural thing to notice about what was going on, a rate of change. And it's very hard to try to go backwards when they already know the rule.
Yeah. And I mean, I was just working with some sixth graders, to think about a more elementary context or middle school context that I think is similar, who we were looking at reviewing, adding and subtracting fractions, and kids who either correctly or incorrectly had learned this kind of algorithm where they drew an hourglass and they were multiplying across and all over. And some of them could do it, could add fractions really well with that algorithm, but struggled with, say, just creating an equivalent fraction and drawing a diagram to show why two fractions were equivalent. And then what do you do there? I think is kind of a parallel question. So I would love to open it up. And anyone have thoughts about this?
I have lots of thoughts. Some of those thoughts are that so much of there tends to be a lot of mimicry in teaching, and sometimes a curriculum program can bring that with the use of algorithms and answer getting first, as opposed to reasoning first. It starts early. It starts, it's pervasive in the sense that in my experience, I have often found that many elementary school teachers don't view themselves as math mindset people, and they're more of a social studies ELA educator. And so they're not really comfortable with flexible thinking, and they still do tend to teach the way they were taught. I just had a support staff member, an English as a second language teacher, walk into my classroom during a math session and completely undermine the lesson and push all of her students to the standard algorithm to multiply two-digit numbers. And in one fell swoop created this dichotomy within the room, and no student that she mimicked and showed this to understood anything that she was talking about, which was wonderful. But they just wanted to get to the solution at that point. They didn't really care about how they got there. And I think with algebra, that tends to happen. There's sort of a race in middle school to get to algebra. There's parental pressure to get to algebra, because if you can get to algebra quickly, you can get to calculus quickly, so that you can get into the college of your choice, and you can score better on assessments, so that you can get into an elite college. And I say that, and Nicole, you may have had this experience at Hanover High School.
I'm familiar with that, yes.
But I just had a 9-year-old fourth grader say that they had to do well on tests so that they could get into an elite college. That was the sentence they said. I have to get into an elite college. So there's lots of reasons. The solution is something like All Learners Network. The solution is something like VMI for all. The solution is something like consortiums of educators coming together to learn and grow. And I think that's what this is.
So the flip side of that clientele is the student in high school who's on an IEP for at least math calculation and a perception being that the discrepancy between what they're capable of and where they're performing on math calculation is significant enough to qualify them. The idea being we need to work on math calculation, but the kid can use, at this point, the kid can use a calculator in their mainstream classes. Yes, they can, but if they don't have the sense of how numbers put together and break apart and factors and all, working with fractions without hitting the buttons that create the decimal version, then they're limited in their upper level progress with math. They're limited to going through a lot of those same routines, getting the answer, and having the math tutor walk through those algorithmic steps again without being able to apply it. So my opinion is that a lot of the math reasoning challenges kids have is because they don't have the structure of the number sense to support them. Number sense not just being, with whole numbers, but how integers operate, how fractions operate, what decimals mean, and so on.
Yeah, absolutely. I think I was just trying to quickly look up a resource, which I couldn't quite put my fingertips on. But I think thinking specifically about what you shared for your students, Pauline, some of those routines that I mentioned from the Routines for Reasoning book by Amy Lucenta and Grace Kalmanik, I think could be really helpful. They have one routine that's called Contemplate, Then Calculate. And basically the idea is there's a quick flash of either a numerical expression or a visual of some type, and kids have to, the quick flash means that they don't have time to actually do the whole calculation out, and they can just are noticing the structure of the whatever it is, and then they have to think about like what might be like a shortcut for actually doing the calculation or counting the total number of things. And I think that's an example of like problems that get away from the same type of problem that they've seen over and over again, which pushes them out of the like, oh, here's the procedure that I learned or mislearned, and trying to apply it. So I know this is obviously a bigger thing than we'll be able to solve tonight, but I think it's super important as we think about the math practices in terms of how can we set students up so that they really are able to engage in this thinking that we know is so important, and at least in my opinion is the most important thing in teaching math more than any one discrete content skill. So thank you. I think we'll go ahead and wrap up quickly. I think if you kind of look at these two practices, we just have this overview here, and the first couple columns are what we've already talked about. But a lot of those, if you remember back to the survey that we did of the teachers and having them describe what their practices were, we actually fell more into what were hopeful outcomes of students engaging in their practices. So if students are looking for and making use of structure, that's going to help them understand why procedures work. To be talking about procedures a little more, it's going to help them choose appropriate strategies, often to solve more efficiently. And it's going to help them view math concepts in relation to each other rather than in isolation. And for math practice 8, again, we get this idea of efficiency. Both practices, I think, really support efficiency, but here it's more around using generalizations to solve future problems more efficiently. If you know that something always behaves like this, then you can apply that and be more efficient. And also identifying or describing mathematical properties and characteristics. So being able to use math practice 8 to describe structures then allows you to then go use math practice 7, where you're identifying those structures that you're maybe more familiar with and making connections to them. And then coming back to this idea of patterns, you saw these quotes earlier. And what I would really recommend is instead of patterns, or maybe in addition to saying patterns, if we're talking about math practice 7, we're really talking about organization, behaviors, and relationships of the mathematics, what's actually there. That's what we mean by patterns sometimes. Or connections between problems and concepts can also be what we mean by patterns. Versus in math practice 8, the patterns really are in the action or process that you're doing, as opposed to the mathematical object itself. And so those would be kind of two suggestions for how to have a little bit more clarity of language when talking about these two math practices. So that brings us to the end of the presentation. And I know, Sandy, I did put this slide in so that you can talk about that. But I just wanted to see if there are kind of any final closing thoughts, again, either takeaways or questions that you still have.
Well, I'd just like to thank you for sharing your handout, because there was a lot of great stuff in there. Like, I'm always trying to connect in the NCTM effective teaching practices as kind of like, that's, how the teacher, or that's I talk about my, the teacher moves versus the student behaviors we want to see. So, by looking at the different representations, that's an NCTM teaching practice, by asking all those questions, that's posing purposeful questions, having the students explain their reasoning, well, that's another, with facilitating mathematical discourse. So you can see all those in that handout of yours, all the things that you're having the teacher do. They just kind of really harken back to the NCTM effective teaching practice. So I thought that was pretty cool. I always like to see that interplay.
Good. I'm glad that's helpful. And that's not a connection I'd explicitly made before, but you're right. It does match up with a lot of those teaching practices.
Mhm.
All right. Well, Sandy, I'll hand it over to you then.
I just want to say thank you for everybody who's here and really mucked around with the math with us. And thank you to Nicole. So this particular conference, or this conference, as well as so many other workshops this year, are funded through some funds from the AOE. And we truly, how wonderful that is for us, so that it's not costing Vermont teachers anything to come and be part of this, because the AOE is sponsoring it. If you go to the ALN site, you'll be able to check out all the other events. If you feel inclined to do so, to post on social media, you know that you can post to Facebook, to Twitter, to Instagram, to TikTok, all of those wonderful places, and just share your takeaways from this workshop. I just want to say thank you. And I just, even listening to what Nicole and you all were sharing, I'm walking away, with more thinking to do about the standards for mathematical practices, and especially those that we just looked at tonight. Thank you. And I hope you have a great rest of the evening.